All right, welcome back. Let's look at a few examples of how to use that limit that we just proved in the previous section. If it's been a little while since you watched that previous video, here was the limit. Here's a little refresher for you. I'm going to write it in terms of x. In the previous video, we talked about it in terms of theta because it was like we were using geometry and angles to figure it out. But theta is just a variable just like x is. So I'll write it as x here. The limit as x goes to 0 of sine x over x we said was equal to 1. And so we need to memorize that because we're going to use that. We're going to use that a lot in the future. Okay? Now, actually, it's a little more interesting than that because basically we can think about it this way. Not only is the limit as x approaches 0 of sine x over x equal to 1, furthermore, the limit as x approaches 0 of stuff like sine of, like, say, I don't know, let's put like a box there, blank times x over blank times x, where we put what you want in the box. That's also equal to 1. Now, if you get too crazy, it doesn't work. But like if you put like a scalar multiple there, it certainly works. Like 5x, for instance, if you put like a 5 in both those boxes, that works, which is going to help us with example A. Or if you put a 3 there, it works, which helps us with example B. Okay, so not only if it's a plane x, but if you put a scalar multiple of x there, it's also true. Okay, and there's other things you can put there, other versions of x you can put there, and it still makes a true answer. Here, let's look at the graph. Here, so we know that sine x over x, the limit's 1, right? Okay, that's what we showed in the last video. Well, what if instead we say put a I don't know, a 10x there and a 10x there. As long as you have the same thing there, notice the answer, the limit is still 1. What about, negative 10? Yep, the limit is still 1. The y values are still approaching positive 1 from the left and the right of the origin. What might break this? I don't know. Like, let's put like x plus 1 there. Does this break it? Yeah, that breaks it. Why? Well, because that's a shift. When you start adding and subtracting, then you shift to the left or the right. Here, we've shifted the whole graph to the left. So the limit now as you approach negative 1, by the way, Desmos is lying there. You can't plug a negative 1 to this function. It does that sometimes. Here, let's see if I hover. If you hover, it says it's undefined. Okay. But if you multiply, by a scalar, that's whenever you still have that same limit. So what if you did like, I don't know, that's x squared. Does that still work? Yeah. Okay. So it works a lot of times, but if you start adding, subtracting, then you're gonna break it. So it works for us perfectly on these limits because, well, here we have a scalar of 3 and a scalar of 5. Okay. So let's see what we can come up with. Now this first limit let me show you first of all what not to do, because every semester I do this and still there's somebody not paying attention and does this on a test, and I can't give you full credit if you do this. I can't give you credit at all because it's incorrect. I'll have somebody that says this, hey, I want to use this limit right here, so what do? I'm stuck with this. So what I can do is, and this is wrong, so don't write this down. What I'll do is say I have the limit is x approaches 0 of sine 5x over x. What I'll just do is I'll factor out that 5. Because we have the constant multiple rule, which says the limit as x approaches 0 of k times f of x is equal to k times the limit as x approaches 0, or c in general. So let's actually put a c there instead of 0 because it works for any value of c where the limit exists. Come on, erase. X approaches c, x approaches c. And so I'll have students who will say, hey, yeah, sure, this is easy as can be. Factor that 5 out, and now we have the limit as x approaches 0 of sine x over x, which now I know that's equal to 1. And so we get 5 times 1, 5, done. Now here's the trouble. 5 is the answer, but that is incorrect how that answer was obtained. And of course, I can't give you credit if you do that on a test because it's just not correct. Like, I mean, you've done something that trig says you can't do. You cannot factor out part of the argument of a trig function. I suppose we do have some identities which allow us to do that. Say like sine the double angle formula. Like if you have sine 2x, you can use the double angle formula. Like there's a triple angle formula, or you could use like some difference formulas, I suppose, identities. But just as is, you can't factor that 5 out. So we have to figure out a way to do this where you do not factor a 5 out. And I think or I know, the key here is our friend of multiplication by 1. Multiplication by 1. This is going to pop up as a theme throughout this entire class. I know that if I can get a 5x in the argument and a 5x on the denominator, then I know the limit has to be equal to 1. But what can I do? What if I multiply by 5 over 5? That's a special version of 1, right? I have not changed the value of the limit. The limit is still equal to whatever it was equal to before. I've only multiplied by 1, which does not change it. But now what can I do? I can use my constant multiple rule, which says, well, first let's do a little algebra before I do that. Limit as x approaches 0. Let's rearrange. I have sine 5x, and by the way, I guess if you want to be really careful, you can put parentheses around that because a lot of times if we're typing it, we don't do that. If I handwrite, I usually do write, with parentheses, just to show 5x is in the argument, and it's not moving, it's staying there. But when we multiply fractions, we multiply numerators, multiply denominators. So this denominator is now 5x. But I still have that 5 on the numerator. But what can I do? Constant multiple rule says I can factor out a constant. I can pull that 5 out front and multiply. And now I have the limit as x approaches 0, sine 5x over 5x. And now I can use this generalized limit, which says that this limit has to be equal to 1 equals 5 times 1 equals 5. Okay, but you've got to be careful. You cannot factor that 5 out. We have to rewrite it with that 5 still intact, with the 5 still in the argument. Okay? But the trouble is that the answer is 5. So if you do it the wrong way, you do get the right answer. But if your method's not correct, then for homework, I don't really check your method, obviously. You do your homework online. If you get the right answer, you get the right answer. But if you're on a test, well, then I'm checking your scratch work. And so your scratch work has to be correct for testing purposes. All right, what about B? B is a little more interesting because, okay, I have a 4 on the denominator, 4x. If I had a 3x there, well, I know my limit would be what? It would be equal to 1. But I have a 4x there, so that's kind of a bummer. But I think we can do a little algebra and, again, use our constant multiple rule. Our constant multiple rule, constant multiple property to save the day for us. So let's see. We have the limit as x goes to 0. Clearly, if we plug in a 0, we get 0 over 0 indeterminate because 4 times 0 is 0. And sine of 3 times 0 is sine of 0, which is also 0. So these A and B are both indeterminate. Okay, so if I start off with sine 3x over 4x, the first thing I would note, and this is going to be a handy tool to have in your toolbox a lot, especially in the next chapter, is that, hey, this is the same thing as sine 3x over x times 1/4. Dividing by 4 is the same thing as multiplying by 1/4. But what can we do with a 1/4 constant multiple? We can factor it out. So this is equal to 1/4 times the limit as x goes to 0. And now we have sine 3x over x. And now we're to the same starting point where we're on example A. How do we need a 3 down there. If we can get sine 3x over 3x, and then we have the limit as x goes to 0, then we know the answer is 1. So how do we get a 3 down there? Well, we strategically multiply by 1, i.e. 3 divided by 3 is equal to 1. And then that allows us on the next step to write this as sine 3x over 3x. But we still, again, we have that pesky 3 on the numerator, but now I can use the constant multiple rule again to factor that 3 out. And now in front of the limit, I'll have 1/4 times 3, 3/4, 3 over 4. So I have 3 over 4 times the limit as x goes to 0, sine 3x over 3x. And now I know that limit is equal to 1 times 3/4. So you get 1 times 3/4, or 3/4 times 1. Of course, just 3/4. Okay. Let's look at example C. Now example C, so A and B, we've been able to take advantage of this generalized limit. I don't see a way to immediately do that with example C. But here is a technique that I'm going to show you, and then you can add it to your limit toolbox. It comes in handy sometimes. The limit as x approaches 0, we have 1 minus cosine x over x. And here is the technique. Multiply by the conjugate of the numerator. Now we had that technique when we were rationalizing the numerator, when we had radical quotients a few videos ago. Now we don't have a radical here, but so we're not rationalizing because there's no radicals. However, a lot of times if you're working with trig functions, if you can somehow get like a cosine squared or a sine squared or a sine squared and a cosine squared, taking advantage of Pythagorean identities is a lot of times helpful. So what I'm going to do here is I'm going to multiply by a special version of 1, and that special version of 1 is going to be the conjugate of the numerator. So 1 plus cosine x. Divided by itself, of course, because that's, to get a special version of 1, you have to multiply by a value over itself. Now, if we do the little bit of algebra here, limit as x goes to 0. The denominator, I'm just going to rewrite as x times 1 plus cosine x. On the numerator, though, if we distribute, FOIL, you get what? You get 1 times 1 is 1. Then you get 1 times cosine, negative cosine times 1. So you get positive cosine and negative cosine. The cosines add to 0. And that always happens when you multiply by a conjugate. The middle terms always add to 0. But then you get 1, so you have the 1 there. Then you have cosine times negative cosine, so you get minus cosine squared. Okay, now what do we know that 1 minus cosine squared is equal to? Okay, think back to trig. Trig, you have your Pythagorean identities. They are very important in trig. They're going to be very important in calculus. We know that cosine squared x, well, usually it's sine squared first. So sine squared x plus cosine squared x equals 1. It's basically the Pythagorean theorem. That's why it's called a Pythagorean identity. But we have 1 minus cosine squared. So what if we subtract cosine squared from both sides? That'll give us sine squared equals 1 minus cosine squared. And just by substitution, we can say equals the limit as x goes to 0 of the numerator now is sine squared, and the denominator is still the same. So it's x times 1 plus cosine x. Okay? Now, we're still in trouble here because we still can't plug in a 0, because if we do, the top and the bottom still turn to 0. So this is still in indeterminate form. But remember, what am I trying to do here? I'm trying to take advantage of my special limit. And here I don't have a composite, so I'm going to use the regular version. The limit as x approaches 0 of sine x over x. Now, we can use properties of limits to separate this into the memorized special limit and then everything else. How can you do that? Well, first, notice that sine squared is what? Sine squared is sine x times sine x, right? That's the exact same thing as sine squared. And now notice what we have. We have sine x over x. And now we can use a little bit of properties of arithmetic to rewrite this as the limit as x goes to 0 of sine x over x. When you multiply fractions, you multiply numerators and you multiply denominators. So we can undo the multiplication and say sine x over x times sine x over 1 plus cosine x. But now we have the limit of the product of two functions. We have a limit product rule. It says the limit as x approaches c of f of x times g of x equals the limit as x approaches c of f of x times the limit as x approaches c of g of x, provided the two limits exist. That says we can take the limits individually. So going back over here now, I can say this is the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x over 1 plus cosine x, provided those two limits exist. I know the first one exists for sure because I know that it's equal to 1. I've memorized it. So that this first limit is the special memorized limit, and that's just equal to 1. Okay? So 1 times, now this limit is not memorized, but I think I can take it via direct substitution. So if I plug in a 0, you get sine 0 over 1 plus cosine 0. By the way, direct substitution doesn't cause any problems because cosine 0 is 1. So that denominator is 1 plus 1 is 2. The numerator, though, is 0. But 0 divided by 2 is not a problem. Division by 0 is a problem. Not 0 divided by a non-zero value. So you get 1 times 0, which equals 0. By the way, this is going to be another memorized special limit for us. So add that to your to your limit toolbox. We'll use that again at the rest of this chapter, and we'll use it in the next chapter when we start talking about these things called derivatives. All right, last example. Example D. All right, example D, we have tangent. Here's just a kind of like a word, a general rule of thumb. When you're doing limits and you see tangents, usually it's a good idea to rewrite in terms of sine and cosine. You know, what is tangent equal to? Tangent is equal to tan x equals, just by basic trigonometry, sine x over cosine x. Now, why should we always rewrite? Well, because we have these two special limits. We have, this special limit, and now this special limit, and they involve sines and cosines. So it's probably a good idea to replace your tangents with sines and cosines, because we don't have a special limit in terms of tangent. We have special limits with cosines and sines. So that's why I always suggest you rewrite your tangents when you're taking limits. So let's see. We could say over here, let's get a little room over here. We have the limit as x goes to 0. We have tan squared x over x. Now, clearly, if you try to plug in a 0, you get division by 0. And it turns out the tangent is 0, so tan squared is 0. So this is 0 over 0 in determinate form. So we can't use direct substitution immediately. But let's see what happens when we replace our tangent with sine over cosine. So this equals the limit as x goes to 0. Now we're going to turn this into a compound fraction, which isn't nice, but we'll fix that in just a sec. So tan squared can be replaced with sine squared over cosine squared. The same thing as tan squared. But now if we want to get rid of this compound fraction business, we can write this as the limit as x goes to 0. Okay, dividing by x, that's like dividing by x minus x over 1. So you have a fraction divided by a fraction, you flip the divisor and multiply. So that means we end up with sine squared x over x times cosine squared x. Okay. And now let's do kind of the same technique as we did on example C. Let's use that special sine x over x limit, which we can kind of see there, but let's separate it out. We can write this as sine x over x, because this is all multiplied and divided. We can write as sine x over x times the remaining sine x over cosine squared x. If I multiply this back together, I would get sine squared over x times cosine squared. But now I can use the product property of limits to take these limits individually, provided they exist, of course, but we'll verify that. So sine x over x times the limit as x goes to 0 of the other leftover portion, which is sine x over cosine squared x. Now, just like before, that first limit is our memorized limit. We know what that equals. It equals 1. And the second limit we can take via direct substitution. It is, well, sine of 0 over cosine squared 0. But, what's sine of 0? Sine of 0 is indeed 0. What's cosine squared 0? That's 1. So we get 1 times 0 and 1. 1 times 0 equals 0. Okay, so that limit was indeed equal to 0. Let's verify these graphically. I think we already did the first one, yeah? Let's do it again. So if we replace that with 5x, now it was over x, we said the answer was what? 5. And notice the y values are approaching 5 from the left and the right. What about sine of 3x over 4x? Approaching 3/4, 0.75. From the right, yep, 0.7495, 7497. From the left, yep, those y values are approaching 3/4, 0.75 from the left and the right. What about example C? Okay, let's make this a little smaller. Example C was, okay, this was different. It was, oh, let's get rid of that. 1 minus cosine x over x. Again, a non-standard trig function, but we can clearly see that the limit, first of all, it's undefined at 0. There's a hole there. But the limit as we're approaching from the right and the left clearly is 0 from the left and the right, which verifies our answer. And then lastly, let's look at tan squared. Tan x here with, oh, we can do this actually. Tan squared x over x. Okay, again, weird non-standard trig function. Kind of interesting, actually. And we can see that there is a hole at 0, undefined. You can't plug a 0 in. But clearly, we're approaching from the right towards 0, from the left towards 0, which confirms our answer is indeed 0. Cool. So we found our limits analytically, and we used the graphical method to confirm our results, which is what the graphical method's good for. You could also use the numerical method to confirm your results, but we found our solutions analytically. That is using algebra and properties of limits. And that's, this is the way, this is like the gold standard way to find limits. You want to use analytic methods. You don't want to bother with tables and graphs, especially if you have no idea what the graph looks like. Now, those, if you have a nice graphing calculator, you can find the limit if the limit's nice. And these limits happen to be nice values, 5, 3/4, 0. But we want to rely on analytic methods. Okay, that's going to be the gold standard, and we'll use graphical methods and numerical methods to check ourselves occasionally, because they're important to know how to do. But analytic methods, that's what the big takeaway from this chapter is how to use analytic methods, because that's what we're going to use going forward for the rest of the class. You need to use analytic methods to find limits at various points in the rest of the class. All right, so in the next video, we'll take a look at a few more examples of using special limits, and in fact, we'll add another special limit to our toolbox. And yeah, if you have any questions, let me know. And if not, I'll catch you then. All right, have a good one.